May I request Akhil Antony to share the screen?
Hi, Srinath.
Hi. Akhil, you will have 12
Mhm.
minutes for the talk, followed
Okay.
by 3 minutes for questions.
Sure.
So I'll probably warn you around 10 minutes. Is that
Mhm.
fine? Okay,
Sure.
go ahead. Thank you.
Hi, good afternoon, all. Today, I'll be presenting a signature from early universe that could solve major anomalies and tensions in cosmology. This talk is based on my work with Dr. Dheeraj Kumar Hastra and Professor Arman Shafilo. So, the archive of the work is given here. Um, So, the standard model of cosmology is largely supported by the cosmic microwave background data from the Planck observation. However, underneath this largely consistent picture, there are certain anomalies and tension that has emerged as a crucial problem for modern cosmology today. These are anomalies such as Allen's curvature problem and various discordances with the yaw redshift measurements. As a solution to these anomalies, we propose a signature from the early universe, specifically in the spectrum of primordial quantum fluctuation. So before that, let me briefly explain the anomalies and tensions present today. The lensing amplitude anomaly or the Allen's anomaly. See, Allen's is a consistency parameter which was introduced as a multiplicative parameter that scales the theoretical prediction for lensing power spectrum. So theoretically, this should be equal to 1. But when we allow Allen's to vary in an analysis with the Planck temperature angular power spectrum data, it has been found that Planck prefers a much higher value. In fact, this value is at a tension of 2.8 to 3 sigma with the theoretical predicted value. Next, the curvature anomaly. So the bending of light can imprint a lensing effect. Therefore, there is a positive correlation between the curvature and lensing amplitude. And it has been shown that a closed universe can solve the lensing anomaly problem. Since the curvature changes the distance measure, it also shifted the positions of the acoustic field. So to bring it back, what curvature does is that it lowers the value of Hubble constant to a very small value, around 52. So this actually further increases the disagreement with the local measurement of H naught, which is around 73.04 as per the latest SHUS release. So also omega K analysis also chooses higher omega M, which increases the discrepancy with the Higgs release also. So the next is the Hubble tension itself. So Hubble constant obtained from the standard model fit to the Planck CMB data is estimated to be around 66 from the Planck TT likelihood and 67.27 from the total likelihood. But the local measurement of Hubble constant from the Seyfert and supernova indicates a value significantly larger than these, which is around 73.04, as I explained, said before, and with an error bar of 1.43. So there is an tension of around 4.4 sigma. And there are also other measurements which prefers higher Hubble constant value, but this has a larger uncertainty. Therefore, they doesn't show much tension with the Planck data. So the next one is the tension in the S8 measurement. S8 is nothing but product of sigma 8 into square root of omega m by 0.3. The clustering and shear analysis provides an S8 of the value 0.77 from the dark energy survey and S8 of 0.759 from the Kids release. But Planck CMP estimate S8 to be of the order of 0.84 from the Planck TT likelihood and 0.83 from the total data. So these anomalies are mainly driven by the TT data. So before showing the solution, let me show the data set we have used for our analysis. So we have done the analysis in 2 steps. The first one is the direct reconstruction of the power spectrum from the data. So what we did was we created a reconstructed a power spectrum that can duplicate the effects, the extra lensing in the CMB TT, keeping L equal to 1. So, and these are the other data sets which we use for the second part. So in the second part, what we did, we fitted the reconstructed power spectrum with the analytical template and calculate the evidence and significance for the same. So let's see how much resolution was happened with our reconstructed spectrum. So the reconstructed spectrum, so this is the form of the reconstructed spectrum. So this one mimics the best fit temperature power spectrum to the Planck temperature data in the standard model plus Allen's extension. Here the red curve is the raw reconstructed power spectrum, and the blue one is the smooth version of the same. So the Allen's anomaly. So when we vary the Allen's parameter along while using the reconstructed parameter as the early universe signal or as the primordial power spectrum, we were able to get Allen's value of around 1.04 with an error bar of 0.074. So this means Allen is equal to 1. The theoretical predicted value is consistent with the Planck data. Also, this doesn't comes with at the cost of fit to the data. So if you see the plot in the next, it is the chi-square CMP Maslow's plot. You can see that the green and the blue plot both overlap over the red one. That is the standard model plus Allen's. That means we get the same fit as a standard model plus Allen's analysis while solving the Allen's anomaly. So our solution doesn't come at a cost of fit to the data. So the next one was the omega k problem. So the standard model plus omega k analysis preferred a low value of omega k and a negative value of omega k minus 0.056, which indicated a preference of 3 sigma for a closed universe. But since this was to solve the extra lensing present in the acoustic peaks of the TT power spectrum, since this is already solved by the power spectrum, our power spectrum, when we do an analysis with reconstructed power spectrum and omega k, we find that omega k comes out to be around minus 0.014. So which brings back the flat universe back within 1 sigma region. So here also we can see that in the right side, the fit to the data is not compromised. We get a similar fit to the data, just like standard model plus omega k. So the third one was the H0 tension. So if you see the gray plot, which corresponds to the standard model, and the green plot, which corresponds to the reconstruction, you can see that there is a clear shift of H0 towards right, towards higher value, without increasing the contours. So this is not just an effect of increasing the contours. You can see a clear shifting H0, which says that our model prefers a higher H0, thereby reducing the tension with the local measurements. So I have also plotted the effect of reconstruction plus omega k on H0. Here also we can see that our model prefers a higher H0 compared to standard model. So the next one is S8 measurement. So in the S8 measurement, if you check the plot in the right side, the band here is the result from the KITS 450 release. So there, the local measurements prefers a lower S8 compared to the standard model, which is the gray one. We can see that when we do an analysis with our power spectrum, the green plot clearly overlaps within the 1 sigma region of the lower redshift measurement. And also, when we introduced omega k with standard model, it created a real tension between the sigma 8 omega m contour of KITS 450 analysis. So when we use our power spectrum, you can see that this tension also can be removed. So basically, our power spectrum was able to select a lower omega m, lower S8, and a higher H0 value. Now let's see if we fit it with the analytical template, how much evidence we can get for this model. So this is the analytical template we propose for the power spectrum. And you can see that it more or less fits the feature, the reconstructed feature. Here the blue one is the reconstructed feature, and the red one is the analytical template. To more or less overlap over each other. Now let's test the evidence of this model. So before that, there was 5 extra parameters added to this power spectrum, a standard model power spectrum. Here P0 is the standard model power law power spectrum. We add a feature of this form. So while doing an initial analysis with Planck-18 TT likelihood, we couldn't find more than 1 sigma significance for alpha 2. So we decided to go with a modified version of the power spectrum. That is, we call it a restricted power spectrum. Here we have set alpha 2 to be 0, and we got the following power spectrum form. And here, when we did the initial analysis, this is the evidence we got for the following likelihood. So when we did an analysis with Planck-18 TT likelihood, that is the TT plus low T plus low E data, we got our new spectrum and the restricted spectrum was slightly disfavored compared to the standard model, owing to the fact of 5 parameters. But when we add the Hubble parameters, Hubble priors to the same, we were able to get a strong evidence for the model. 3.4 for the restricted and 2.67 for the new spectrum. 3.4 is because it got lesser number of parameters. So here are the posteriors for the parameters we introduced. We can see that when we add the HST priors to the TT likelihood and the TP is the full likelihood. TT, TE, plus low T plus low E likelihood, we are able to get more than 3 sigma significance for alpha 1. That is alpha 1 equal to 0 is rejected with a confidence of 3 sigma. So,
Akhil, you have 2 minutes.
2 minutes. Oh, sure. These are the posteriors, and you can see that there are about all the parameters has been constrained properly. Next, the correlations between the anomalous variables. So earlier we mentioned about the anomalies, Allen's anomaly, omega k, omega m, S8 and H0. And we can see that with our power spectrum template, when we did the analysis with the P18, we were able to find that Allen's equal to 1 came back within 1 sigma region, omega k equal to 0, the flat universe came back within 1 sigma region, and omega m and S8 preferred a lower value compared to the standard model, and H0 preferred a higher value. So clearly reducing the tension between the corresponding local measurements. So this is the evidence for the various data combinations we used. We were able to find strong to moderate evidences for our model when we used the Hubble priors with the various various data combinations, and the confidence level that is with the how much significance we were able to reject the standard model is around 3 sigma, that is around 99% in all the data combinations. And here we can see that when we add BAO and the SN, it gave a lesser evidence than the standard model, because BAO and SN actually prefers lower omega m because of higher omega m, because of which the parameter space moves towards standard model, thereby reducing the evidence. Yes. So these are the posteriors for the parameters for different data combinations. Here first 4 corresponds to 2 sets of data combination, and the next 4 corresponds to 2 other sets of data combinations. In all these cases, you can see that alpha 1 has a significance about 3 sigma. That is, the standard model is rejected with a confidence of 3 sigma. So next, excuse me. So this is basically same analysis. So next, this is the best fit power spectrum we got for the 2 data combinations. This one is the full data combination TP, ACT, DH, BAO, SN, and HST, and for P18, TT plus HST. So the red one is the one for which we get the highest evidence. So we can see that this is of a similar frequency and located at the same scales. So such a power spectrum can actually solve various anomalies and tensions present in the Planck data today. So let me conclude. So a simple shape of primordial power spectrum obtained through deconvolution solves the lensing amplitude anomaly. The reconstruction also solves the closed universe anomaly and brings back the cosmic concordance. Importantly, we find that a solution to the anomalies within the Planck CMB data automatically resolves or greatly reduces the tension between different data sets. And our analytical power spectrum model, the new spectrum that is designed to match the reconstruction, prefers lower matter density, lower sigma 8, and higher H0. And this was not just enlarging the priors, the contours or anything. They clearly preferred higher H0 value, lower sigma 8, and lower matter density. When the new spectrum and the restricted spectrum are compared with the Planck temperature data with priors on Hubble constant, we got moderate to very strong evidence for the models compared to standard model. The proposed form of power spectrum stays consistent with the small-scale CMB measurements from Atacama Cosmology Telescope Observation, large-scale structural measurements from the Dark Energy Survey, and a recently estimated age of the universe from globular clusters. Thank you. So,
thank you, Akhil. Do we have time for maybe one quick question? Yes, Sriram.
Akhil, the couple of slides back, there was a blue and a red curve, power spectrum. This one. The spectral tilt on the left seems to be considerably different.
Spectral tilt on the left, you mean the red one?
Of both, of these two spectra seem considerably different.
Yes, yes. When we add the HST priors, it's actually chooses very NS value. It was around 0.98 actually, compared to the the full data. When we use the full data combination, it preferred an NS value around 0.976 around. I don't remember the number exactly, but as for all the cases, the NS chosen by the model was very high. So around 0.98 to be 978 to be on an average.
Okay, I understand. Thank you.
So the Hubble priors, when we add, it automatically prefers higher NS. Higher NS actually, yes.
I understand. Thank you.
Thank you, Akhil, for the interesting talk.